I'm a lead software engineer at EPAM. I worked here for 2.5 years. And currently I'm on the SAP security account. So I lead some developers, I do some programming, and I'm very interested in Node and Node.js and also system design, which is why we're doing this kind of a little bit more high-level presentation. And my name is quite strange. I know, it's because I'm Norwegian. I'm not Indian or something like this. I know people see my name sometimes and they don't see my face. They think this guy must be some Middle Eastern. It's really strange, but I'm Norwegian. And yeah, I live in Poland, Warsaw, and I moved a couple years ago, really like it here. But before we start the presentation, so we have this word in the title, which is called reliable Node.js systems. A reliable system is essentially a system's ability to function correctly and consistently over time. We have a very long description here, but essentially it means that when we have an input into the system, and we have an output, what it produces at the input and the output is the same over some time period. So it doesn't change, it doesn't go down. It's available. So if you know the CAP theorem, it's essentially the consistency and the availability portion of the CAP theorem. So it's available and it's consistent. And it doesn't change over time. It doesn't change with different inputs. The system stays the same and the system stays available. And then we have a couple of things in this presentation which we will talk about a little bit later, which is graceful degradation. Essentially what it means is that if we have a system which is very low on resources, so Node.js, the reason we bring up the last point about degradation is that Node.js is not so good at handling very high memory intensive tasks, right? So it's good at doing things in isolation, but when it comes to long running processes, high memory usage, it's not so good at that. So essentially the reason it's important in Node.js is because, this brings me to my next slide. It's a single-threaded system. There's a lot of memory leaks, a lot of things can go wrong. We can have unhandled promises, poor memory management, long-lived processes which kind of doesn't finish. And so a lot of things can go wrong and also get stuck somewhere. In other languages, this is not as key of a feature because we can more predict how the memory is going to behave, but with Node.js, we kind of throw some code in there and we know that it's going to create some objects and it's going to do some things, but we don't necessarily know how efficient it's going to be. That's why we kind of talk about this reliability. Things can freeze, things can exit slowly. And we also have a shared memory space. So there's a lot of memory leaks going on here. We have an example, which is, let's say we have a Node.js system. We have a basic system. It has 2 different Node.js servers. We know from doing some kind of testing beforehand that this system can handle around 10,000 requests per second for each one of those servers, right? And our average request per second is 12 to 15K. So we have a reliable system. We know how much it's going to take. We know when it goes down. It's a good system. As long as it's consistent, as long as nothing happens, as long as the whole system stays put, it will handle the load that we give it. It's even above the load that we give it. And so, but the problem is what happens if one of the servers goes down. So we said each one of the servers has 10K RPS per second. One of them goes down, we have an overflow. So we have 12 to 15K requests. The other server goes down, it cannot handle the load. There's nowhere to load balance it, and the whole system goes down, essentially. So this is a very easy example. Of course, the system doesn't behave in this way normally. This is 2 servers and a load balancer. Probably no one posted into production, but this wouldn't work, right? So the question is, how do you prevent the loss of data and how do you prevent downtime? These are the 2 things. So one of them is the fault tolerance from the CAP theorem, and the other one is the availability of that system. So I said that this system, we shouldn't put it into production, right? It's not ready. It's too simple. So the first thing that you start doing, if you are, let's say you're a junior or a mid-level Node.js developer, you say, okay, so when this server goes down, I have my 2 servers, I have my load balancer. When this one server goes down, I'm going to try to restart it, right? Because we have a memory limit. When it hits that memory limit, we're going to try to restart it, right? And this works. The problem is just that if the server is doing something while you restart it, of course, all the data is going to be lost. So you're going to have corruption. You're not going to have, a reliable system. Essentially, the fault tolerance part is gone, or the reliability and consistency is completely gone, because you had data. You had someone who was trying to, let's say they were doing a shopping. This was a shopping application. They're doing the checkout system, right? and they were checking out, they were buying their order and paying for it, and then the whole thing is gone, right? So the one server is gone, the order is gone, the customer is not getting the order. So this is not a very good way of doing it. It works because we will get the system up and running again, we will restart it, but we will have some kind of corruption of data, right? We will have lost data in some way. But it's kind of like the naive, let's say, junior approach to doing it. The thing which we want to do instead is that we want to do something called a graceful shutdown. And what does this mean? So essentially what it means is that when we close that server and restart it, we're going to try to wait for it to complete the whole task queue before we do the restart, right? So we're going to wait for it to close the connection to the DB. We're going to wait for the flush of logs. All the resources is released because we have this event loop. So essentially what I'm saying is that we're waiting for that event loop to finish, or waiting for the process to finish, and then we close it. So this is a little bit better than what we did earlier. We're restarting the server, but we're waiting for everything to finish. We're waiting for it to close, and the system will be up and running again. Of course, if the system has too many, like the next time the system reaches this low, the next time the server goes down, we're going to have the same problems. It doesn't really fix it. It just fixes it momentarily at that point where we kind of had the issue going. And so this is kind of the left thing that we're doing here. This is the restart. So, and like the thing that I'm getting to now is that there's essentially two different ways of doing it. There's a restart, and there's the thing that we do in the classic kind of Kubernetes clusters that we have now is we just spin up a new pod, we reroute the traffic. And on the left side, we're kind of doing this restart, so it's the same pod. And on the right side, you know, we have a new pod that we're starting, but it's essentially the same thing as doing the two of them. But sometimes we get a bit confused and we say, okay, we spin up a new pod, but they're essentially doing the same thing, right? So the left side is essentially what we would do with PM2 or like some older methodology. We would, you know, restart the server. Right side, we just spin up a new pod and we do everything again. And then the question is related to the previous slide is, like, how do we know when an instance or a pod is down? So if we go back to the first slide, we kind of assume that we know that the server is down. Like, we assume that the load balancer here knows that the server is not responding. But this is actually something we have to implement. It's not something we just know. We don't just know that every single server or the status of a server in a cluster. Like, we can see it on a drawing, we can see that it's down, you know, I make the red border, but in reality, like, we have to do something to actually make this server, to know like the availability of that server. In any system, how do we know if an instance or a server is down? The best way of doing it is a health check, right? Like, we don't want the manager to come to us and say, hey, your whole system is down. We want to know that it's down when it goes down. I mean, of course, sometimes the manager comes and says it's down anyways, but yeah. So we do something called a health check. And this is a very, very common practice, especially in Node.js. In other systems, not as much, but in Node.js, we do that all the time. So what do? We have an endpoint. Essentially, it can be called /health, can be called /health, it can be called /abcd. It depends on whatever you want to call it. And what do? We have something called a side. Okay, so this is a little bit more complicated, but we have something called a sidecar for the load balancer, which is essentially a smaller server. It's a smaller memory unit, let's call it something like this. And it's continuously with some interval checking if the other node service is responding, right? So it can be every 5 seconds, it can be every second, it can be every minute, it can be every 30 minutes, whichever interval we want. But the main point is that it's checking the health regularly of that service. This way, if something is wrong, we can do what we did earlier. So we can know that this server, because in a system, not every single server is always going to have traffic, right? Sometimes you have a server which it doesn't have any traffic for a couple seconds, couple minutes, and then all of a sudden we get a huge burst of requests and it has been down for 5 minutes and we couldn't really know. So we can do what we did earlier here. We can do a health check on it. We can continuously ping it. If it's down, we do the restart or we spin up a new pod. And this is something where, like, if you have worked with Kubernetes or other, even PM2, other type of kind of scaling solutions, you probably do this automatically. Like, you have implemented this in some kind of system because this is such a basic kind of thing to do. But a lot of people or a lot of systems that I worked on, we actually did not implement this because we just didn't know it existed. So now you know that it exists. And yeah, so what is the health endpoint going to return? It's going to return you 200 or 500. So 200, everything's okay. 500, something's wrong. restart the server, spin up a new pod, something's wrong, check it, diagnose it, etc. And this is also kind of a load balancing strategy where if we have a rotation of services, we don't necessarily need the server to, it can take some time to restart the server, right? So we probably also want to get rid of it in this rotation for the load balancer. Like we want to take it away so we know that it shouldn't be there until it restarts, and then kind of, get it back up and running. And we have like a small example here. I don't know if you guys have ever used Nest.js, but this is something called Terminus. We use this in my project right now for every single service. We have something called a health check service. It implements it for you. It pings an endpoint, and then you know that it's working. And the module, we can kind of set the intervals for it, but essentially it's just doing a check. It's just doing a get check, right? Like you don't really have to make some kind of magic for this. It's just pinging with some interval, checking that it exists. And if it exists, it does a refresh of it, right? But then the problem is, I already answered this, but what if the traffic is irregular? Like what do we do if, so from the first system that we had in the beginning, we are assuming that the system has 12 to 15,000 requests per second, right? But what happens if it has 100,000? The whole thing goes down. And there's no way for us to implement it because we only have 2 servers and they handle 10,000 requests. So 100,000 requests per second, the system would just completely fail. And then you will get a message from your manager, like someone else said earlier, because this would be an extended kind of shutdown. The whole system would be down until we have increased how many requests per second the system can do. So if you have a very, very basic system like this, there's no way we can scale to 100,000. If this is kind of the metrics that we assume that it can take, there's no way we can scale to this. The whole system would just be down. But what we can do instead, which is probably what a lot of you guys are doing, we implement auto scaling, right? Like we scale the system. We have some kind of Kubernetes, we have some kind of pods. You buy more buy more servers on the cloud. You increase the memory automatically. Something happens when we reach this limit, so we can still kind of hit the count. So this is like the most obvious thing that people do. If you ever had like some kind of system design talk, the first thing that people say is, okay, so the thing is that the first thing, if someone ever asks you, what would you do if the system has a very irregular load or a lot of load? You say, I scale it, right? And this works, this is great. We should scale systems, but it's not the way to actually make it optimal because it costs a lot of money. That's the main part. It costs a lot of money. It's also hard to monitor a system that has many clusters, too many pods. It gets unreliable the bigger it is. And so, yes, we want to scale it, but there are some better ways of doing this, right? There are some ways that we can do this over time because we don't necessarily need to scale the whole system now, but we can handle the request over time. And we're going to look at that now. So like I said, all this is great in theory, but there is one kind of component. So essentially, like if this was our system and I had full control over the system that I create, like this is my in-house system, I'm only interacting with my in-house services. Every single service that I own, that we have, I own it. Then I can just auto-scale it. I can fix it. If there's some memory problems, we fix the memory problems. We use some indexes on a database. We can change to Node.js from Node.js to another language if we need to. Like we can do things if it's in-house, right? Like we have to find a good database solution, but we can generally speaking fix it if it's in-house. But there's one problem, and that is it's great in theory, but what if we are working with remote servers? Probably you guys have all worked with like some kind of remote server that has a rate limit. You don't control it. It's buggy. It's laggy. Like you have some kind of team. There's 5 people on the North Pole and they are like maintaining a server that you need some information from because your manager told you need to use the server. And it's completely unreliable, right? Like how do you work around this? The rate limit is 100 requests or something absurdly low. Like there has to be a way to work around it. And this happens quite frequently. And there's a couple ways we can do that, so the first thing which everyone should do is if you're working with some remote server, you need to decouple it from your system, right? If you're going to send requests directly to that system and just expect that it's the response, that's probably not going to happen. Sometimes there's going to be something that's lost. The server is going to be down. So you need to introduce some kind of queue that decouples it from your server. the other thing that is very common to do is that we retry it. So if something goes wrong, we do the same request again, we retry it until it works, right? So we do we can retry it 100 times, we can retry it 200 times, probably don't want to do that, but we can retry it. The problem with the retrying is that, okay, then we hit this rate limit that I talked about earlier, but here, if we are introducing some kind of queues, we're introducing some retrying mechanics, we're going to make this remote server a lot more reliable, right? So we have this thing called a rate limit. So each second, it can also be per hour, it can be different. So essentially the reason that you do this kind of thing where you have an overhead of how many requests the system can handle is because we talked about it earlier, right? With our requests per minute. We know that our system can handle 12 to 15,000 requests per second. Let's say we have 100 users, so we have to spread how many requests our system gets for those users. So if we have 100 users, we would have 1.5 thousand per user maybe, or okay, this is very oversimplified, but let's say we would allow each user to have 1,200 requests each, right? So then we have a limit, so we know it's 12,000 or 15,000. We spread out among our users, and we know the system is going to behave reliably. We know it's going to work. And that's why we have a rate limit. So when you're working with remote servers, they almost always have a rate limit. The problem is, if we all of a sudden hit this rate limit from our side of the system. So we made this queue. You can see this queue that we have. We queued up the results. We're waiting for it to get available again. But all of a sudden we hit this rate limit, and we hit it every single time. We have way too many requests coming into our system. The rate limit is like I said, it's like 100, and we have 10,000 requests coming in. How do we solve this? Or can we solve it? Maybe we can. Maybe we have to ask them for a larger rate limit. But there are some things we can do to prevent this. So there's one thing which every single system that has kind of the structure that I showed earlier with a queue and some remote service should have. Probably also systems when they interact with each other, like inside the system with a queue. It doesn't have to be a remote service. Everything has some kind of queue and reacts with something else. So it should have something called a circuit breaker. And what is a circuit breaker? So we talked about this manager earlier today, right? Or earlier in the talk. If your whole system goes down, your manager is going to come to you and he's going to say, hey, how long does it take for us to stabilize the system and get it back and running? Might be down for an extended period of time, but he's going to come and he's going to say, hey, how long until we can get this up and running again? If you haven't implemented what is called a circuit breaker, you probably wouldn't know how long that would take, and you probably also wouldn't be able to give him an estimate. You might not even be able to stabilize the system, because essentially what happens is we have in this diagram I showed earlier, we have what is called a cascading failure, right? One part or one service goes down and it takes other parts with it. And that happens very often. A circuit breaker is essentially a way to prevent that. So what happens is that if one service gets rate limited, it closes off that service completely from the other parts of the system, waits for it to normalize by introducing a rate limit inside that service, and then reopens it. So essentially we are waiting for that part of the system to normalize, for the rate limit, for anything that is, whatever is happening inside that one to get stable, and then we're allowing traffic slowly to go through it again. And the reason for this, like I said, is because if you try to just hammer this server with like thousands of requests, you're just letting everything through, it's just going to crash. It's not going to work, it's going to crash, it's not going to, and it's going to take the whole system down with it. So generally speaking, you always want to have a circuit breaker if something goes wrong. And we can open it fully. At the end, we can open it half. We can open it 1/3. We can open the service as slowly and as we want. But the main thing is that when we do this, we don't introduce cascading failure, right? So on the left, on the right, yes. On the right, we have, again, very basic implementation. It's something called, something called Opossum, which is a library that implements circuit breakers. We introduce a timeout threshold, an error threshold. So essentially how many errors, because the system can have errors for many reasons, right? It's not like every single error that comes in means the whole thing is wrong. But most likely we have a threshold for when we know that there's going to be too many errors. If you have 10,000 errors in a service that is handling 100 requests, probably something is wrong, right? So we have a threshold for 50 here. We have a reset timeout for when this circuit breaker should kind of stop, and some different methods. And then, so now we talked about kind of how to make it work. So essentially we went from something very basic and how we can make something a little bit better. to if something fails or if a part of the system fails. And now we are at the part where, like, let's say you implemented everything that we have had in this talk so far. Of course, it wouldn't be enough. Like, you would make your system more reliable, you would make it more consistent, but it's never enough to make it always function, always work, never go down, to just always keep being consistent, cap theorem, etc., etc. So let's say, like, we implemented everything that is in this slide. We implemented even more. We auto scale it. We do all these nice fault tolerant things. But you have 10 million new users the next day, or even a million new users next day. You have 10,000 users, now you have a million users, and your system just cannot handle it. You don't have the budget. You don't have the capabilities to do this for whatever reason. So the whole thing goes down. And so if the whole thing goes down and you are not prepared for it, we can actually predict this as well, which is insane, but we can actually predict when everything fails. And so when everything fails, we do something called load shedding or graceful degradation. And what is load shedding? So essentially, we proactively reject or we delay low priority requests. So in like a high-level system, we have many different endpoints, right? We have many different services. And some of these services might have a much higher priority to our overall system than other services. So we might have some that are, okay, let's fetch information about a given food. Let's say we have a shopping app, right? Like, we have a shopping app again. The users are making some grocery shopping. The most high priority endpoints for this service is probably the endpoints that allows the user to actually buy those food items, right? And then we might have other things related to the statistics of the system. We might have other endpoints related to just getting more information about the tomato, like, let's say, how much a tomato weighs, how many tomatoes are in a given store. But generally speaking, the user probably won't care as much about these things as just being able to shop the food that they would like. And also, like, if a company, for 2 hours, 3 hours no user is able to buy any food, we lose a lot of money, right? But we probably won't lose so much money if we don't know how many users are using the system at a given time or how much a tomato weighs. If they can buy the tomato and they can get it into their cart and ship it to them, that's most important. So when everything fails, what we do is that we bring down, for some time, parts of the system. We have circuit breakers. We have different things that kind of normalizes those part of the system. And we wait for it to, hopefully come back online again. And this way we avoid the whole system overloading. We maintain at least the core parts of the service. We make sure they run. We make sure the application functions in a very, very intense high-load environment. And we also probably need to drop something. So if you have the most normal thing to do in this scenario is that a lot of applications have internal cron jobs that do different scheduling tasks. So the cron jobs might do things like move information about the users, like I said earlier, to some different services. It might do some migrations. It might try to stabilize the system in some way between two services. This is kind of the first thing that goes. All these cron jobs are usually pretty heavy. All the metrics, all the logs, we drop them. And then we kind of get to the other stuff where we deprioritize the critical endpoints. And so the thing that we have on the right side is just a mock. It's just if we have a really, really large amount of requests, we just don't allow the user to use this endpoint. We have some kind of statistics job, some kind of statistic endpoint. It has a really, really large amount of requests. We have some kind of limit. We just don't allow people to use this endpoint anymore because we cannot handle it. We know that's the max and we just simply reject it. And then at the end, so this is it's easy to look at all the things that we talked about now and kind of be like, okay, this is really nice in theory. We have like all these different things that we implement and they work together. But these are things that we use. So I mentioned in the beginning that I'm on the SAP account. These are things that we do every single day. And these are scenarios that we have seen happen every single day. So we can give an example first before we go to the drawing. When I started on my project, the current one that I'm on for SAP, we didn't have a circuit breaker implemented. Our application had all the other things that we have in the slide. We had a really good system. It was highly available. Everything was working great. But our users are growing a lot, right? So we went from an MVP to being kind of like a core service within the infrastructure SAP. And so our service grew by 10 to 100 times the traffic in around 8 months. And we did a lot of different things to optimize the services. We did performance on the database. We indexed the data. What else did we do? We decoupled them with some queues. We made sure that the endpoints are quick. We did auto scaling. We did all these different things that we talked about, right? So we thought, okay, this service is going to scale. Everything is going to be great. All the users are going to be super happy. And we're never going to take down all the SAP pipelines for 40,000 developers, by the way. But of course, this didn't happen. So we ended up taking down the pipeline for 2 hours almost because we didn't have a circuit breaker implemented. What happened was that it wasn't about the users. So when we talk about these things, we normally say, oh, if we get 10,000 more users, everything is great. No, we had a bug. Someone had put a retry inside a retry. So we had a queue that would be retrying, and then we had an endpoint that called that queue that would be retrying. And essentially we went from having 10 retries to having 200 retries for an endpoint. And if you have 10,000 requests, 200 retries, there was an error. There's a lot of retries. And so that's what happened. We ended up having a lot of retries. We had a rate limit at the same time for Docker Hub that was a little bit too low. And the whole system was rate limited. We didn't have any circuit breaker implemented for the service. It took down everything else. And it took us a long time to stabilize that because we didn't have a way to implement or to stabilize a specific service. So what we had to do is we had to go in and we had to implement the circuit breaker while the system actually wasn't working. It wasn't super difficult because we were using Kubernetes, so we had this kind of sidecar thing that we talked about earlier. We could just put a YAML script in every single kind of service and it would do this, but yeah, it took down the whole thing for extended periods of time. So yeah, it's a good reason to have a circuit breaker because our system was nice, it had good load, it could handle all the data, and we had good indexes, but everything else was not working. And then so this is a real-world example of one of the systems that I work on. It's a little simplified because we're not going to go into like all the details of the system that we work on. We have, of course, a lot of different things that we're doing in this one. But we're combining some of the things that we talked about in this presentation. So what are we combining? It looks really simple, right? We have a coordinator service. What does the coordinator service do? It interacts with the remote service, but it doesn't interact with it directly. It interacts with it through the queue. The queue has a sidecar, or the coordinator service has a sidecar, but it actually has a sidecar, and checks the remote service. It also checks the scanner service for health checks and makes sure that they're all up and running. Inside the scanner service, we have kind of divided it into different steps, into different parts. So we have 2 Node.js processes that are running at the same time. It's nice and organized. And we have the same for scanner too, right? And whenever these finish, they communicate with an event bus, which goes back to the coordinator service, goes to the persistence layer and puts it on the database. All the services have a health check. All the services have some kind of queue that they communicate through. The event bus has a queue. The remote service has a queue. And the queue itself has a circuit breaker. There's no way to actually show the circuit breaker on the slide, but all the queues have a circuit breaker. I hope they have a circuit breaker at least. And so the thing is that if you implement all these things that we talked about now, going back to the kind of like the beginning of the slides, it's not that you're magically just going to support 5 million users. Or 10 million users, or whatever. You're going to support the max limits of your system, and you're going to increase it. So let's say your max limit is 10,000 RPS, like requests per second. You're going to increase it, you're going to make it more consistent, but you're not necessarily going to, support an increase of 10 million users per day. But if we do these things that we talked about, we will make the system more reliable. We'll make it scale up to the limits of what we have in that system. So for the system that we have here on the drawing, we know that the limit of how many users we can have is 40,000 because that's how many developers we have at SAP. We cannot exceed 40,000. And then for each one of them, you make some calculation. You know that, okay, each developer commits to the pipeline maybe a couple times per minute per team and then per team. So you make some averages, right? You make some assumptions. And you know almost how many requests you can handle per second. You make the system so that it can support 10 times that, accounting for any bugs. And then you hope that you don't have some kind of spike somehow. Like you don't have someone who, like in our case, implements a retry into a retry, and then you exceed the rate limit of Docker Hub and everything goes down. And that's kind of how we do it. We just scale it, we implement some nice features, and then we hope that that we don't do some mistakes along the way. And yeah, that's kind of it. Thank you guys so much for listening.